Mark P. Otten back with you.
Okay, this is your path analysis in R video. Let's get into it. This is going to be a relatively small model compared to some other path analyses that might be out there. Just 4 variables. You see them on the screen there. It says plugging it into SPSS. Well, we've already done that. I've already done that. And so you see the numbers that came out when we did that. It was a regression of trait anxiety being predicted by whether or not you are an LA driver with a 0.10 beta there, not significant. Another regression with driving anxiety being predicted by trait anxiety in LA driver. The trait anxiety path was highly significant. The LA driver path was not. 0.66 significant, 0.06 not significant. And then finally, a third regression, risk-taking behavior being predicted by driving anxiety, negative 0.03 not significant. Okay, so we found all of those. Those are betas, regression coefficients in SPSS already. So why are we even here? Well, number one, to replicate those numbers in R. But number two, R will give us fit statistics and some other things that SPSS will not. And that's the latent variable analysis part of this. Even though we're not actually analyzing any latent variables, we're just analyzing a bunch of measured variables, 4 of them to be exact. We're going to be able to get some fit statistics here, and then those are the same fit statistics that we're going to use when we start turning variables into latent ones later on here in a little bit in this class. So first of all, I've got your code here that I'm showing you. There's a couple of steps before running it that I need to show you, however. First one is that I imported the data from SPSS into R, and what I did was I just deleted everything from that data. This is from the 534 path analysis data set that you're going to be using in your homework, but it's different variables. So same process, similar process, different variables. And so what I did in SPSS before importing the data into R was I just deleted everything except the 4 variables in question here, the 4 variables that are going to be part of our analysis. I just did that for simplicity. It makes it a little bit easier when we get the to read when we get the covariance matrix here in a second. You can leave everything in there if you want, if you'd rather. But I like to try to simplify my data set as much as I can before doing latent variable analysis or importing it into R or both. So that's number one. Number two is down here in the lower right corner of R. I selected the Lavaan package. You just check the box there to install that, and it will do so automatically. By the way, that's LA latent VA variable AN analysis. Lavaan. It always reminds me personally of a guy named Lavaan who was in my first grade class. I wonder whatever happened to him. It was spelled differently though. Maybe he's off somewhere doing latent variable analysis right now. I don't know. Anyway, so select Lavaan, import your data, and then you're ready to type in your code. And I've just got the code typed out here to show you. I'll take you through it briefly and then we'll run it and see what happens. This first line here is COV for covariance. We're going to get a covariance matrix out of this, and it's just the covariances that exist in the data set, and then we're going to be able to compare that to the covariance matrix implied by the model. And when we do that, make that comparison, that's the foundation for SEM, and that's going to allow for our fit statistics, ultimately the chi-square test and such. But like a lot of researchers will skip that step if they're just trying to get to the results. I like to print those covariance matrices up front just to see what things look like. And also because it's part of your homework, I need to show you how to do that. So that's that first line, just the covariance matrix from the data. So I will run that, and it's just going to give us a little, let's see, can I make that? That's okay. It's going to try to improve the formatting there. But it's basically just a 4x4 matrix with our 4 variables. In the top left, for example, you see 0.25. That is the variance for LA driver, the variable. For here, for this one, 0.02, that's a covariance for trait anxiety and LA driver. And then that value repeats here for LA driver and trait anxiety, like the reverse, but it's the same thing. So there's a diagonal here of variances, and then above the diagonal, the numbers should be the same as below the diagonal. You just really need the one or the other, not both sides of the diagonal of that matrix to go forward. So anyway, that's your covariance matrix from the data. And then once we make our model, which is this set of hypotheses, this diagram over here on the right, once we make that, we are implying a certain covariance arrangement by our model that we can then compare to our real covariances. So by the model, we are hypothesizing a relationship between LA driver and trait anxiety, thus implying that there is a significant covariance, or when we do a regression, represented by a beta there. And so then when we get the covariance matrix from the model, we can look and see, okay, is there there should be a relationship implied by the model, right? But is there a relationship actually in the data? And that comparison, again, is the foundation for structural equation modeling, latent variable analysis. Okay, so I have my other video on path analysis gives you a little bit more of the theory. Let's get on with the R. Okay, so the next step here is to specify the model. I called it FWY 210 model. That's in honor of my favorite freeway in Southern California, the 210. Feel free to name it after your favorite freeway or something else. Anyway, the point is that whatever that first part, whatever comes before dot model is up to you. That's the name of your, whatever you want to call your model. And then the dot model tells R, okay, we're going to run some sort of regression or something else here. In this case, multiple regressions forming a path analysis in total. These are those regressions, and the beginning of this statement there is a single, it's an apostrophe. It's not a quote, it's just the one, it's the lowercase quotation marks, I guess you would say, or apostrophe. And then there's another one at the end here, the statement. And then in between are the regressions. You can list them out, you can format them differently here. I just tried to format them one per line. So the first one, trait anxiety being predicted by LA driver. Second one, driving anxiety being predicted by both trait anxiety and LA driver. And then the third one, risk-taking behavior being predicted by driving anxiety. Should match your diagram. And then this statement here is like, let's get a covariance matrix from this data, from this particular model, or a estimated covariance matrix so that we can compare. So we're not actually getting our betas, our regression coefficients, and our fit statistics until the bottom line here in summary. Summary will give you standardized equals t that specifies your regression coefficients and stuff, and then the fit measure, fit measures equals t that specifies you want fit statistics. So I'm going to go ahead and run everything else in one swoop here. If you're okay with it, I mean, even if you're not, I'm still going to, I'm not talking to anyone, I'm just talking to a computer. So I'm going to go ahead and do that. If you have questions about any of the details here, and of course you might run this kind of thing and get an error message. If you get an error message, let me know what happens. R usually tries to tell you in its own language what happened, but one key, by the way, here is just to use the data, the name of the data set, whatever your data set is called. And so if you just download the data from Canvas, it's going to be something like X534 path analysis. The X is at the beginning because R doesn't want the first character of the file name to be a number, so it puts an X in there automatically. But anyway, that just needs to be consistent with the first line here of your covariance matrix. And then I've got FWY210 to represent my model here multiple times. So that also needs to be consistent along the way. Other than that, you can kind of copy paste and go along with those last two lines of code. Okay, so let's run this part. Okay, so we got a bunch of stuff here, and I'm going to scroll back up to the beginning of it. The beginning of it is the covariance matrix that is implied by the model. So we've got a 0.233 for the model implied variance for trait anxiety, and a 0.166 for the model implied covariance between trait anxiety and driving anxiety. You just got to watch the headings here. I think they're in a little bit different order than they were for the actual data covariance here. Yeah, LA driver came first. So to match it up, you can just kind of go ahead and bounce back and forth, or just rely on the chi-square test later to tell us how similar or different these are. Just for example though, driving anxiety, trait anxiety, by the model, that's the strong one. That's the 0.66 here. The model implied a 0.166 covariance for that relationship. And in the actual data set, we had driving anxiety and trait anxiety 0.166. So the model is very close to reality here for this strong effect. It's representing the effect very well, which you might expect from the fact that the path is so strong. There's a strong relationship between those two variables. It shows up in the actual data covariance matrix, and then it also shows up in the model implied covariance matrix, for example. And there's some smaller numbers down here to represent some of the other paths. Okay, so that's all I'll say about that. Basically, in your homework, you just need to report these matrices and move on. Moving on means looking at the regression coefficients and the fit statistics. So I'm going to kind of skip to the bottom or close to the bottom here where the regression coefficients are. Start with that, and then we'll bounce back up to the fit statistics. So, does this match SPSS? Well, we got to look here at the standardized std.all column. So I'm going to try to make this bigger, improve the formatting just a little bit. Is it going to work? No, because I ran it with the other formatting. Okay, I'll just leave it like that. All right, so let's look for this 0.66. Where is it? Okay, under the regressions, it is going to be in the std.all column, standardized.all, standardized values. So it's standardized regression coefficient, and it's here 0.658, which should be under driving anxiety, trait anxiety. Well, it is. It's just kind of flopped over into the next row here because of my formatting, but it's there. The 0.095 is the first one. That's trait anxiety and LA driver. That's 0.10 in the SPSS, so that matches up as well. 0.060 is the next one. That is driving anxiety and LA driver, 0.060. And then the last one here, 0.028 negative, is the last regression coefficient, negative 0.03. So it just comes in rows there, and you just need to match it up that way and look at the std.all column, and you'll be okay. And maybe your R screen will be wider, so it will actually be formatted better than mine was. The variances here below that, that's where you're going to get your e-values or your epsilon error terms. And so epsilon is the notation. It's the leftover variance after a particular dependent variable has been predicted. So they come in there's three of them here. The first one is trait anxiety. There's a 0.991 for trait anxiety. There, that would go along with, you'd have a little arrow pointing to it, and you'd say 0.99. It's a large value. The smaller one here is 0.556. That's for driving anxiety, suggesting that we have predicted more of the variance of driving anxiety successfully. And then 0.999 is the last one for risk-taking behavior. So those are your error values. And then bouncing back up to the fit statistics, that's the last piece here. Let's see. Okay, so you just got to make sure that you are selecting model test user model for that's the chi-square, 6.963 with 2 degrees of freedom, and a rejection here, 0.03 p-value. If you select the baseline model, that's different. That's the baseline model where no variables are related to each other. That might be used for comparison, but it's not going to be, that's not your chi-square. Chi-square is 6.96 in this case. Model test user model, of course. And then we got the other test statistics here. Whoops, I almost went too far with the CFI, comparative fit index 0.965, and the RMSEA, root mean square error of approximation 0.102. And then in the notes for path analysis, I have more on what those all mean and how to interpret everything. Meanwhile, that is your introduction really to latent variable analysis in R. And a path analysis to start us out with 4 variables. The models will get bigger, things will get more fun, I promise.